Hi, everyone.
Hey.
Hey.
Say hi back. I know it's early. Hopefully everyone's had the chance to get some coffee and maybe dig through some email while we were setting up the slides here. But welcome to sort of Data Science 101. We're going to aim this talk at a wide range of skill levels where we'll kind of delve in and give you sort of our insight if that's what you're interested in, but then also cover like really basic concepts and hopefully simple words, because I like simple words. And that way, yeah, we can cover sort of everyone's skill level, and hopefully everyone comes away with this with a little bit more knowledge about data science, a little bit more excitement about the tools that are out there in the common libraries, and just the sense that a lot of this is more approachable than maybe everyone thought. So, just from that standpoint, we're going to start off with kind of a journey through some wrangling with a data set that will be new to hopefully most of you, and it was new to us not that long ago. And then we'll do some visualization, we'll do some modeling, and then we'll get some takeaways from that. So one thing we get at DataRobot, we work with a wide range of customers, but a lot of our customers are actually pretty skilled. And so for the ones who aren't as skilled, there's all these advanced features in the app for doing this and doing that with models. And for some, you can read about that online, and that's fun. But at the same time, it's really tough to figure out where do you start along your journey of data science. You can take some edX courses, some Coursera courses, but at the same time, you feel like you're just dipping your toe in the pond, and it's tough to kind of get that breadth where you can see all the different paths that you can go down before you choose one. And so I would say the best way to start is to load up an editor, get some basic packages, and just try things. A lot of people who do data science now, because it's a relatively young field, they started, many of them, in grad school trying things. They were a bio researcher and they said, there's some tools out here that I can use. I'm not really a computer scientist at heart, but with some know-how, some elbow grease, and a lot of patience, I can figure things out. And so I think, personally, that's the best way to learn some data science know-how. And that's kind of the journey that we want to take you through with these slides. So without further ado, let's get started. Let's meet our data set. So this particular data set is interesting. I'm sure all of us have seen one of those USA Today articles. US students score 25 in the world in math, and then some education expert gets up there and says, the world's coming to an end, American students are falling behind, something along those lines. Well, this is one of those data sets. We decided to focus our particular subset out here on students from Mexico, because interestingly enough, for this particular year, there were the most participants from Mexico, and the data is relatively clean, and it's relatively cool. So let's look at that. There's one file that has student exam results, and this is a look at student exam results. We'll explain sort of how these Pandas calls work. But as you can see here, there's the subject heading, this is math, the test year, and then this particular overall question, population pyramids, has several sub-questions. As you can see, there's a lot of missing values. We don't know yet whether those are skipped, or maybe that student just didn't take tests in 2000 or 2003 at all, so that's something that we'll have to explore later perhaps. But we can see when they've scored, so they got a question right, or they got a question wrong. Simple stuff. We also have biographical data. So again, this is not the entire span of the row. We're just grabbing columns 10 to 20 to give you a quick sample. But for an individual student, we have their sex. We have something about ISCED, which ISCED will be the attendance at school level that's been achieved, education level that's been achieved. So here, did they attend preschool? Age they started primary school? Did they repeat a grade? Was there a mother at home, a father at home when the questionnaire was administered, etc.? So where do we begin? Let's say we know some Python. That's a ground level. There's some tools out there that we can use, that we can experiment with. But the first thing we have to do is get our data into our Python environment and then start working with it from there. So let's start with the basics. So reading data from the disk. So first thing you want to do is import Pandas. Pandas is obviously the library that you've heard about. Wes McKinney is here. You should go talk to him about it if you want absolute details. But here, we can use Pandas to get our data into our Python environment using this read CSV function. We've just linked our path to our data, both CSVs, the score tests, the questionnaires, and we put them into separate objects. That'll be important later for when we want to sort of combine those, but for now, that's a simple place to start. So this read CSV, based on the title, I think it reads CSV files, but what were those output objects doing? What is that? How can we use that? Well, it puts the data into a data frame. And a data frame is this important concept of sort of relational tables, which you'll see in just general database theory. You'll see it in R, because that's what everything in R seems to be based on. It's a really useful way of organizing your data. And so Pandas is really important in a lot of sort of data flow pipelines in Python, because it uses this core abstraction to help us deal with all the data that we have, and provides like a sort of universal format to pass things in and out of different tasks that we want to perform. So here, just an example, we have a data frame. We can call it the head function that we saw in a couple of slides earlier, and now we're able to operate on this with all the tools that Pandas gives us. So CSV isn't the only way to get our data in. We can use text, Excel, JSON. Maybe you've got a wonderful multi-million-dollar Hadoop cluster with HDFS set up. You want to use the wonders of deep learning with your infinite resources. Go for it. As they say, deep learning can't fail if you have enough depth and you have enough computing resources. So maybe that's the path you want to take, but you have to get it into your environment first. So let's start simple. But what's really in a data frame? So there are series, which you can think of as one feature, one column. And then the data frame itself will be a collection of series, a table. One thing that's important to think about if you were designing, say, a library or a set of tools is you want to be able to keep things flexible. You want to handle when someone passes in one series, sort of one column, but also handle things perhaps in a different way if there are multiple columns. So that's managing defaults and then different computation paths. So the designers of many of the libraries that we'll look at have taken that into account, and that means that it's much easier for you, the end user, to do things.
Oh,
Do we have ODSC bloopers? Can we put that in? Cool. Okay, so many series can be combined, and then we can put those into a data frame object. And then again, a data frame object you can break into several series, and then perhaps construct a data frame that has a subset of those features. Let's say you found some features are very informative, or let's say you have control over some aspects of a system, and you want to make a data frame which you can pump into a model, which will be the factors that you can control, so that you can see, okay, to what degree can I actually modify this system and the target variable that I'm trying to target. So Pandas provides all sorts of functionality for these data frames. You can go look at the documentation, but we're going to show you some of the basics in the following slides. And like I said, when you're thinking about designing a framework, hopefully you've taken into account the fact that users might want to do a range of different things, and Pandas has done a fantastic job of handling those. So now let's access data in a data frame. We can get one column just by specifying the label there. Always label your series, or if you're working with a larger data frame, label the features. It just makes it so much more readable when someone's reading your Python notebook, or you're trying to figure out what on earth you were doing. Figuring out, from your data dictionary, what the hell's in column number 7, or column, God forbid, number 120 is always a bitch, so go through that. And then a subset of columns. Here we found student ID, and then school ID. As you can see, the first view, we're grabbing the head here, so the very top of the data frame here. All the students are from the same school, so maybe this is nicely ordered. You won't always find that, but at least in our little sample here, we see that. And so here we have another taste. This is looking at when school ID is equal to 2. So we can put in a condition very easily.
So do you mind moving that footnote to the speaker?
Oh, the speaker?
Oh.
Sure. We can rotate it a little bit. Is that better? I think that's all we can. It's sort of taped to the floor. Sorry about that.
Sorry.
So you can pass in conditions. What Peter Preprocessing, who's one of my favorite data scientists here at DataRobot, calls Kung Fu, NumPy Kung Fu, Pandas Kung Fu. And you can pass in rather elaborate conditions as well, and slice your data in a certain way in one line, which can be really convenient. So this way we're looking at just this particular school, what's going on. As you can imagine, hopefully the country codes are lined up. You won't always see that in real data because people sometimes enter things wrong, or the data is noisy or it's missing, but we get what we expect.
Yeah, and for those who have some SQL experience, like this is a where statement in SQL. So if you say like where these columns has a particular value, this is how you do it in Pandas.
So now we know a bit about data frames, we know a bit about why they're important, we know that they're a great sort of universal object where we might want to keep our data and then plug into different things. So now we can move on to bigger and better tasks. Like EDA.
Alright, so I'm going to talk about probably my favorite part of data science, and that's exploring your data. I want to say this is probably the most important bit of being a data scientist. You really need to be very familiar with your data. You kind of really want to understand it before you feed it into some type of model. So the model's going to go and churn away and give you predictions, but if it doesn't know maybe some things like the relationship between the variables, what variables are important, and so on. So a few things you want to look at in EDA. The most simple being like, let's say some survey gave you some survey data, insisted that the data was randomized and properly collected. But you go in, and look at it, it's like, oh, it looks like there's a lot more, female versus male or something like that. It's not properly randomized, not properly collected. Then you're gonna have to go back and recollect your data. You need to know that before you go into modeling and things like that. You also want to understand the type of variables in your data. Do we have a lot of numeric variables? Is it, a lot of categorical? A lot of text. You want to know those kind of things. Another important bit you want to look out to is like, do I have more predictors, more columns than I do rows in your data? Or do I have more rows than I do columns? That's going to affect what models you're going to use and choose and it'll work well when you start modeling. Okay, so the first thing you might say is like, okay, let's just dump the data frame into the console and just look at it with my eyes. Maybe I could get something. Well, you can see here, that doesn't work very well. You kind of see, oh, there's a bunch of numbers, but we don't know, like, is this a normal distribution? Is this somewhat skewed? You really have no idea what you're looking at here. So Pandas provides some nice functionality for you to kind of dig a little deeper and understand your data a little better. We've already talked about head a bit. That'll just take your data frame, print out, the first n columns. There's also a tail, which will do the last few columns. That's kind of good. Like maybe the first columns are different than the last columns. Maybe your data has a particular order, and so you can kind of just take a look and see that real fast. There's also things like info and describe, which will tell you things about high-level statistics about your data frame, as well as kind of the values inside your data frame. So here we have info. And so info kind of tells you some high-level things. You can see the first column tells you the number of rows. We have roughly 40,000 rows. The second tells you columns, so we have roughly 200 columns or so. So that's a lot of features, and you might kind of think, okay, maybe we're going to have to cut that down a bit. Maybe we can't handle that many features, or maybe some are less important than others. So we're going to have to do some reduction of our data before we even get to the modeling stage. And one column I actually really like here is the dtypes column. a row. That tells you kind of the type, if it's numeric or not. So we have 32 floats. Those are usually decimals. In your data, we have some integers. Those are usually categorical variables. And then objects is kind of Pandas way of just dumping everything else. So this might be text data, it might be categorical data, or it might be malformed data. But that's everything else. But we kind of have a rough overview of what we're looking at here. Some numeric, but mostly text probably in our data set. The describe function is going to give you a lot of high-level statistics. This is very useful if you want to kind of, yes?
What's the memory usage?
Oh yeah, so that's how much size and memory your data set's taking. So kind of how large it is. So you see here, this is 66 megabytes, which is not too large. You usually have 44 gigs of memory.
Data frame is in the memory.
Excuse me?
Data frame is going to be the memory or it's on the disk?
This is in memory. So I mean, it'll be in disk as well, but when you have a data frame loaded up in your IPython session, it's going to be sitting in memory.
Yeah, this is like the Python object in the IPython session, or if you were doing like interactive Python. Yes?
So is there a limit on the size of the data frame? Since it resides in RAM?
So it's kind of limited by how much RAM your machine has. If you try to load something up with more RAM than you could handle, it's gonna crash. There's things out there like S-frame and stuff that deal with data frames that don't fit in the memory. So there's tools beyond Pandas that kind of try to mimic Pandas in a way. They use to handle data that's too big. But for a lot of cases, especially when you're doing EDA as a first pass, it's nice to kind of take a small little subset of your data and look at it so it can fit into memory. Because doing stuff in memory is a lot easier, especially on the EDA stage. Now, of course, it might be different once you get more data, but as a first pass, I'd recommend kind of putting it into memory, or a subset of memory.
Hopefully a few samples so that you have a good sample. Go in and check to your sample like that.
That's right.
If your data set is too big, can you add some function to load only the sample, automatically sample?
To see how big it is? Oh,
When
well,
you import the file.
so when you're subsampling, just how to subsample, is that what you're asking? Yeah, so you usually don't want to take the first n rows, because if there's some order, that's going to be bad. So as a first pass, you guys just randomly sample. You could also kind of look at, if you know what your target variables, make sure you sample in a way that, if it's classification, for example, to take equal number from both, or if maybe there's some groupings that you look at. So, you can do some fancy things depending if you know the data or not.
It also depends on your output modeling.
Questions and also speak up loudly because there's lots of people behind me who probably can't hear as well.
Sure, will do. Thank you. So he asked what happens how to subsample your data. If it's too big to fit into memory and you want to fit it into memory, what's the best way to go about doing that? And my answer was, there's a few different ways, but a lot of times you don't want to just take the first n rows or the last n rows because, there might be some ordering, you might miss some things. So, random sampling is a good start, or sampling in a way that if you look at your target variable to take equal numbers from both. So
Or not necessarily equal target numbers. If you know that your modeling task is going to be dependent upon, say, a certain distribution, like let's say you have a particular test, or you're looking at advertising data and only 1% of your clicks are affirmative, they clicked, most of them are no's. Well, then you're going to want to perhaps sample such that the distribution matches the distribution of things that you're actually looking at. So it might be highly skewed, but you want that skew to carry over in the sample that you look at.
That's right. Okay. Well, let's go back to the scribe a bit. Let's talk a bit about that. So this is kind of high-level statistics, things like means, minimum, maximums. This is kind of good also to get an idea of, like, does this data work? For example, if you were told this data, let's say, had dates from 1970 to present, you notice that the minimum date value is 1980, then something's probably a little wrong in this data set and you need to go back. Or, for example, if it's skewed or so on and so forth. So it's good to get a high-level idea of that. You also see here we have a lot of NaN values on these columns, and it's easy to see right there. So the next part is, we said we have two files. We have this biographical data file, and we have this exam file. And so when we do our modeling, we want to combine them into one big data frame because we can't kind of deal with these two things separately. And so a common thing to do is to merge two files together, take two data frames, stick them together. So we said we have this student ID field, which is the unique ID field. Now, of course, when you're doing your EDA, you want to make sure that that is in fact unique, because it could turn out like, oh, we thought it was unique, but if you look at the value counts, and maybe there's like less than the number of rows or something along those lines that are not the same. So that's something you always want to do before we insist that it's a unique value.
Yeah, for data like this, you particularly want to look at, make sure that the student IDs, for example, are unique overall instead of just unique per school. One of the most common, like, simple transforms that you'll see people do is, let's say that the ID is dependent upon another ID, so you can chain those IDs together, for example. So say do school ID dash student ID, and so you'll see variables like that, and so then that gives you a unique reference ID to use everywhere else.
All right. And so that's where those high-level describe functions and stuff come in very handy. Okay, but in this case, student ID is unique, so we're gonna combine with data frames on that. And so Pandas has a nice little merge function that you could use for that. You could give it 2 data frames, in this case, exam and bio, and you could merge them on a particular column, and that's student ID. It'll take that, it'll look in the rows of one set, the exam set, look in the rows in the other set, and match on student ID, and put those together into one big row. And it'll sit in memory as a single data frame. And that's, oh, okay. I forgot. So we did a bit of pre-processing for you in this demo. That basically took all the scores, the exam scores, and only took science scores, math scores, reading scores. There was more columns in there, but we kind of wanted to take it down to a subset we wanted to use. And so we took all the scores and put it in a data frame. Just as a note, if you're looking online on Pandas tutorials and stuff like that, you'll see a lot of these DFs running around. And it's just a nice little thing to call your data frames DF. It stands for data frame. In this case, we call it score DF. It's a common convention. Okay, so we have this score data frame, we have a bio data frame, and as we said, we merged them together with this merge function. You take the first data frame in the first argument, the bio data frame in the second, and say, okay, I want to combine it on this column, student ID. And it'll give you a single data frame combined together that we're going to go ahead and use for modeling and supplying.
Just a quick question.
Yep.
Your score DF has total score, that's the column tag, and then it has totals. So where is the totals coming from?
So in the data frame or in your data, there's a total score column. But there's also these math scores and these reading scores and these science scores. They're kind of labeled, I think, in the data as like reading score X. And we took those, aggregated them together, and put them into a single column. Now, we're going to release some of this code later on so you can see how we actually went about doing that. But for now, just kind of think of it as the scores per test, science test, math test, and so on. Total scores and an aggregate of all of those. Okay, and so maybe we want to get some summary info of that data frame we just created. There's a particular column called reading enjoyment that's kind of telling you like, oh, do I enjoy reading outside of class and how often do I do it? And there's this value count which will tell you each count of the values of each level. You can see a lot of people, only read 30 minutes or less. That's not too surprising, and then people reading a lot, very few.
You can see there's that one character that isn't being parsed properly. And this is very, very common when you're taking a data set from the wild, per se. And so that's kind of an indicator when you're doing your initial EDA, oh boy, I might have to do some cleaning. I might have to basically do other kinds of handling to make sure that this renders well and will play well with all the different transforms and graph and everything else that I want to do later on. So consider that as like a warning sign.
Also kind of the magic of read CSV, the fact that that loaded it up with still malformed characters. One of the nice things about Pandas is that read CSV function's been designed very well to read, a lot of malformed data, which is really nice. Okay, so just a quick aside, I'm going to keep bringing it up, is that missing values are something that we're going to have to handle. There's a lot in this data set, and just to count them up, there's this nice little is null function. And so what it'll do is it'll tell you what values, when your data frame, it'll take your data frame matrix and put a true value there if it's an NA value or a false value there if it's not. Pandas has a nice functionality to kind of detect NA values, common NA values, and kind of fill them in for you. You should always kind of make sure it's using the right ones. For example, when I used to work, we filled a lot of NAs with like -9999. Pandas isn't going to pick that up. It's going to think it's a numeric value. So you might need to go in and tell it what the NA value is. But for most common cases where you have this strands or missings, it'll pick it up for you. And so we've just gone through and summed at each column to look at the NA values, and there's a lot, especially for these categorical variables like repeated, grade, and at-home mother, and stuff like that. So we're gonna have to deal with this later. Okay. So now the interesting part, right? So we're modeling to get relationships. We want to see if there's relationships between our, the total score and our other variables, but we also want to see, if there's relationship between our predictors. Some predictors might be, duplicates of others, or they might be very correlated to each other, so they're going to play a role together when we do some feature engineering. And Pandas has a lot of tools to deal with that, that we're going to talk about coming up. Common ways of covariance. Truthfully, I'm not a big fan of covariance because it can be very misleading. A common example of a misleading covariance is kind of clusters, right? If you have a bunch of clusters of points, their covariances might be gibberish, but they obviously do have some relation. There's a cluster there, and you wouldn't see that with covariance. And so the best way to do it is to just take a look at these variables and see what's going on. And I think Brian's going to take a bit and talk about plotting with IPython. Let's see.
Yeah. Just want to say IPython notebooks, like the one that we're actually using for this talk, are really good. You can put the plots in line. You can easily show someone a lot of plots quickly. You can change them, iterate. So just a quick plug for that. And then this is the quick command to get your plots to render nicely.
Yeah, I just kind of want to make that this presentation is actually an IPython notebook, and so all you see is what's going to happen with IPython, which is a wonderful environment.
That also keeps us honest, because there's not that much magic.
Why do you use inline in our notebook?
So inline, typically it's up to you. I mean, inline will just put it like as soon as you call it in there. It's kind of what I'm used to using, to tell you the truth. I don't really have another reason besides that.
The notebook also renders it, but gives you interactivity.
Yeah, so if you want that, go ahead. I'm not going to tell you to use inline or notebook. It's up to you and what functionality you want. They're both great.
Awesome. So we have two sort of classic choices. Well, one is more classic than the other. Matplotlib is the go-to for plotting. I'm sure many of you have heard of it. You get a lot of control. It's also significantly more difficult to use. I personally prefer Seaborn. It's hot, it's new, it's from Stanford. Doesn't mean it's necessarily good. MIT. But anyway, it makes things really simple. It takes in data frames. You can graph things easily. We'll see sort of later on that doesn't necessarily mean you won't want to go in and then change some of the defaults, but sensible defaults are great. So we'll move forward with Seaborn for the most part. And we can just import Seaborn as SNS. If anyone knows what SNS is actually specific, or is that an acronym or something like that, I've always wondered. Googled it, I haven't been able to find out. So if anyone has insight into that, I'd love to know. Please see me after. Scatter plots, the old Excel tried and true. We can view relationships between X and Y. Seaborn has rather nice scatter plots though. They'll actually do the scatter plot, but then there'll also be a little bit of a heat map, and then the sort of distribution plot on the side. What they generally recommend is their joint plot. So this joint grid here, we can see cultural status, or this sort of economic status proxy aggregation along with home possessions. And we sort of see what we expect, which is a good thing. One of the things that I was getting at earlier, the tools that we need for good data science, patience, curiosity, common sense, and then healthy skepticism. I'm initially skeptical of a lot of these sort of features until we've looked at them. And then dug in more, especially at different levels of granularity. So this kind of confirms that hopefully this isn't all garbage. We have home possessions here, and then this is cut off a little bit. But down here, we have the index of economic status, and there's a general sort of trend where having higher socioeconomic status correlates with more home possessions. One thing that I want to dig into is, what does home possessions really mean? This one sounds important and objective, at least it sounds that way. Index of economic, social, and cultural status. But home possessions is actually something that counted how many iPads are in the home. We might be missing something. Home possessions could be anything, so that's something we might want to dig into later. That's just my thoughts upon seeing this graph.
Right, and just another point I want to make about looking for correlations, you also kind of want to look at if there's maybe proxies of variables. So for example, like, let's say we're trying to model score later on, and let's say there's another variable that's a proxy to score, it's exactly equivalent. If we model with that variable, we can get great models, but it really doesn't mean anything to anybody, because it's basically just a copy. And so you have to make sure with these plots and such that maybe you can get rid of those variables and make a good modeling data set.
Yeah. Josh, can we adjust?
Resolution?
It's been fine so far. Maybe it's just that we stack too much on the slide. It might actually be cut off. Yeah.
What
question?
you're showing there is on the side and on the top is the distribution, the histogram, right?
Yeah, so this is the distribution here, the socioeconomic index, and then this is the distribution here of
But
possessions.
that's automatic with the joint plot. You don't.
Yeah.
Okay.
Yeah, we don't have to specify that.
So the joint plot will take a scatter plot in the center, and then the distributions on the x-axis is the top one, and the distribution of the y-axis is on the other side there, automatically. Now the one thing that we did do differently, you can see we specified the kind of joint plot to be hex, and what that does, instead of a scatter plot where you get a dot per point, it basically makes little hexagons in your thing and bins it by those hexagons, so you kind of have almost a heat map where the number of points in that hexagon gets darker, which is a little nice because you kind of get a 3D view where you kind of have dark spots being high frequency values and light spots being low frequency, which is better than just the mounds of points on top of each other, which is very hard to read.
And just to kind of reiterate that we want to look at things before just assuming that things are or are not garbage, or that the trends that we might expect actually show themselves in the data. Here we have total score and then socioeconomic status. So one of the things that was perhaps most interesting when approaching this data set is to say, okay, does total score of a particular student have a really strong correlation with their socioeconomic status, at least among these students from Mexico during these 3 years? And it seems like not really. Students are all over the board. You'll see there's definitely a real sort of small sort of center there where, okay, among students of lower socioeconomic status, they tend to be more closely and densely bunched there among that particular score group. But it seems like after you pass, this level of socioeconomic status, they kind of fan out and they seem to be all over the place around this center of the score pattern. So that kind of helps dispel any notions that we might have had, preconditions about what's going on here. So again, this is sort of helping to look at and help us frame how we think about this.
Yeah. And also just on the staying skeptical part, you can see there's kind of like little breaks in that total score. And we're not quite sure what that is actually, but it makes kind of us wonder maybe how this data was collected. Did they just decide not to take scores out of it? Did they ground, what's going on? And if this was your actual data set, you might want to go to the person who collected the data and say, what's going on here? Should I be worried? Or, I don't know.
Yeah. You had a
I
question?
was just going to ask about the no data columns.
Yeah, no, that's very interesting. We saw that in the plot, a slide or two ago too. So yeah, it's definitely a bit concerning. I want to go, we looked at this and we were able to find a reason that made sense for it. So yeah, we want to go ask the curators of the data. That's really important because total score is one of our most important features that we want to use for prediction or things later. So the fact that nothing weird is happening there is an important thing for us to track down.
Sometimes what happens is that things get rounded up a little bit, so there's almost no 29 and a lot of 30. So
Yeah, no, that's definitely a possibility, but we'd have to find that out.
The difference between this plot and the other plot, we're using joint plot, was the way we're treating that.
The difference between this plot and the other plot is just the variables that we're using. So this one was using home possessions and socioeconomic status, and the other one's looking at total score on the exam and then socioeconomic status. Otherwise, it's the same. Now, another old standby, histograms. Seaborn does well here. It's better than just taking simple averages. You know, if you just take an average, a mean, you don't know what the distribution of things are. You don't know where there's crazy outliers. Josh was talking about earlier how at his old job they used to code things -999 when they were missing. Well, if you just took you know, some views of the data, you wouldn't really see that. But a histogram will let you sort of see that and say, okay, that's definitely weird. Let's take care of that. Another thing is when looking at things that you expect to be related, you expect their histograms to look sort of similar. So we're actually going to look at, say, male, female for a particular, you know, a couple areas of just maybe total score. And then we'll see, okay, we expect scores to be around sort of the same distribution. If one is way off, then we have to question our data as well.
And also, you know, going back to the target, which is kind of a special place in the modeling, you kind of want to look at, an average doesn't tell you if it's skewed or not, or the shape of it. And, you know, depending on the shape of it, you might define your metric of how you're going to train your model differently. So it's very important to understand things beyond the average for these distributions when you're doing your model.
Or it might define, okay, we might want to actually do some pre-processing to fix that because some models won't handle that well at all. Here we have we show the group by function, so grouping by male and female. We see that females higher average overall with the means, and then more in the center groups. There's more men doing poorly. There's a few more men in each of the higher percentiles, but the main thing that this confirms is that these two look sort of similar, and so hopefully we don't have to dig in and then figure out if anything's wrong. This doesn't necessarily work so well if you've got a ton of different things you're trying to chart at once. Here's a rather complicated one, and this actually does show us a warning sign. So here, all the students grouped on grade 12, they have this massive peak around 38. Why is that? You know, was there a day where, say, all the students of a few particular grades missed the exam, so they coded them all with, you know, perfect 38s or, you know, high scores, or was there some sort of cheating involved? Why is that just massive? Maybe they had one question which was dead easy, which you know, would comprise the entire test, and all you have to say was true is the sky blue, and that gave you 38 points, and that's why everyone has 38 points. This is concerning. This would be perhaps a reason to dig in more or exclude grade 12 from analysis, because you might think, okay, patterns in grade 12 shouldn't look maybe that different from grade 11, and then so on and so forth. All the other things show things that look, patterns that look way more sort of predictable. And predictability when modeling is always a good thing. We had talked about the shape earlier, and a lot of you know, convention says, okay, looking at sort of shape and outliers and stuff and determining, okay, mean, median, what's going on with the crazy ends, you want to use a box plot. Seaborn has these really nice filing plots that enable us to both look at things that might be, say, bimodal, which box plots don't do very well as sort of more conventional things. So, big yes on filing plots. Use them and use them well. Here we're looking at the high schooling of the father and its impact on total score. So didn't complete primary school, completed primary school, high school, college, and then graduate level, and then further and beyond whatever degrees those are. You can see that the sort of biggest bump in between them is basically finishing high school and then finishing college. That gives a big bump to the child's score, but there's not as much of a bump, say, between didn't finish primary school and then finished primary school. We don't see any sort of bimodal peaks or something like that, but that does come up in real life data, and violin plots would be a good way to see across multiple distributions, okay, are those extra modes happening in sort of the same way, you know, across many of them, as opposed to doing each individual histogram separately and then sort of lining them all up and then seeing what's going on.
Yeah, so here we kind of see like across the different levels, like, oh, it looks Gaussian roughly, you know, just with a shifted mean. So it just looks like as you go up the levels, we're just shifting up the mean, but the distribution is very similar. Where you could imagine maybe level 2 has like two two nodes, one where like they don't do well and one where like do very well, and there's kind of a difference between that particular level. You might want to treat that special.
Another thing we can do is use Spastic Grid. So we can look at interactions of things. Particularly, it's good for like Booleans or categories, large categories where we want to see multiple distributions, but they don't sort of flow all sort of side by side nicely like you would want to do in a violin plot. So it's better for like decision making or something like that. Here we're looking at gender, and then the distribution is total score and whether the mother is at home or not. And we can see if the mother's not at home, for both male and female, we see a peak at lower scores and then kind of a long tail there, whereas things seem to be more normally distributed if the mother is at home, and the mean is definitely higher. So again, I confirm some common sense there, but this is a really good way to kind of put all those together. One thing that's interesting about this is you can see that the bins are all rather large. The resolution isn't that good. And one thing that I would like to do is, for the ones that I'm saying are sort of peak and then long tail and then sort of normally distributed, I want to dig in and then see if there's anything crazy going on in any of the bins. So looking at this, what I would want to do is, okay, let's go up the resolution and let's see that, this, as I increase resolution, does what I think it does.
And just kind of as an aside for your different variables, like a lot of the models when we get to that kind of make assumptions that the variables are normally distributed, that they kind of follow a bell curve, and they kind of are very sensitive to that. Especially if you get into like neural network training and stuff like that, yeah. Gaussian models very important. And so you can see here, these really aren't Gaussian, they're very skewed. So maybe I want to transform these variables. Maybe I want to transform them or something like that to get them more normally, or just center and scale them. And so that's kind of important stuff to know before feeding it into a model.
Yeah, so maybe actually looking at means is kind of the big picture that we want. Maybe we've looked at our distributions, we've said, okay, this is normally distributed, we don't have any 999 codings, or we've cut that out, outliers aren't a problem. Then what can we do? What's sort of the biggest impact, top level, bluff, big line up front that we can show to make sense of this? And we can use these Spastic grids. Is that, yeah, that's cut off a bit.
It's yes and no. That's
Yeah,
the bottom.
So here we can just see yes and no for at-home father, and then it's grouped by sex. So we can just very clearly see better than the distributions because we'd have to sort of look at the center, whereas the mean also include that in the stats. Just top line, do students do better if the father is at home? Yes, students are doing better. You can see that males get a bigger bump than females do, but both groups of students do better.
Is the little
Yes.
black thing the confidence interval?
Yes, so that actually what they're doing there is assuming a Poisson distribution, and so it's saying that's the mean value plus or minus this, which is nice to have because you can say like, oh, that's a very significant difference on the left plot, right?
Yeah. So since that they don't overlap, right? So
Yeah, no, so that's right. So that black line, Seaborn does it directly for you. It's very useful when you're making statements like, oh, there's a difference. Like, is there really, or is it just a statistical fluke?
And then we can also do a grid with 4 choices here. You have to, I don't know if anyone can read this, but this is no mother at home, no father at home. This is father at home and mother at home, and then yes, no, and then no, yes. So just top line, yes, compared with no mother, no father at home to mother and father at home, students do significantly better. The bump is bigger for mother at home compared to father at home, but no mother. Again, good things to know, apart from just the distribution, looking at the means just for like general guidelines. Heat maps, so if you want to do categorical against categorical, you want to perhaps do a pivot table, do some aggregation, look at what things that would be interesting here would be how many students fall into like individual groups, and then also looking at how scores are kind of mapped across different groups of categorical variables. So that would be another sort of state of analysis that we want to do before, say, picking something as our target and then expecting things to perform as we expect them to perform. here, we're just taking a pivot table, throwing it into a heat map. Seaborn makes this really easy. We just took the pivot table, put it in with annotations, format false. And here we have, do they like to read nonfiction books and how much? So how often do you read? A few times a year, once a month, never, several times a month, several times a week, and the same for fiction. This is rather hard to read just given defaults because never is right in the center, and you would think never is reading less times than a few times a year. So we can easily reorder that, not very useful there. With display order, you just pass that in to our P table, which will reorder it, so it's just reordering based on the names there. And now we can see students who read fiction several times a week and never read nonfiction actually did the worst. I don't know what you want to confirm or deny there. I don't know, do tablets count as fiction, or what's their definition of fiction at that point? I think it's self-defined by the students themselves, but clearly that's a warning sign. Students tend to do better, it looks like, when they're reading a moderate amount. They're here in the center with a slight trend towards a little bit more nonfiction than fiction. Not sure that these self-defined statistics are quite as useful as some of the other ones, but it's definitely interesting to look at, and it'd be fun to look at small subgroups instead of the larger group of students and see, okay, what are the trends among boys, what are the trends among girls, what are the trends from students from a particular school. Maybe some schools show more predictive value than others. Here's another aggregation. Here we're looking at basically how many students fall into these categories. So this is really important when interpreting the heat map from the other side. The greatest number of students say they never read. So maybe students actually feel like they read a lot, just by, I would say several times a week is sort of descriptive, but I mean, it's relative to how you feel about it when you're answering the question. Not that many students fall into these categories where they read tons of nonfiction and almost no fiction. So you could say, okay, there's not enough values here across all of the data to really say predict something like that. That was your target. Now the magic. So we've done some EDA. We now have a much, much better idea of what's in our data set. We've taken it, we've looked at it, we already have found some troubling things. Now let's see if we can do some predictive models. Let's see if we can make this useful.
Okay, so I'm going to talk a bit about this. Although I have to say I really like EDA. I can't stress enough how fun EDA is and stuff like that, and how you should use it. But going on to modeling, probably while you're here, the most common library used in Python is scikit-learn. It's a great library. It kind of has a lot of different machine learning algorithms baked in there for you just to grab and use, from linear regression to neural networks, GDMs, whatever you want is usually in there. Also, things like clustering we talked about. There's a few algorithms there like k-means, DScan. And I mentioned also that we have a lot of features, so we want to do some dimensionality reduction based on kind of variance of these guys, and those are in scikit-learn as well as preprocessing. We have a lot of null values, we have a lot of text values. We're going to have to deal with those, and scikit-learn has some tools for you to make your life a lot easier, so you get to modeling faster. To import scikit-learn to get it into your Python environment, it's as simple as just doing import sklearn. You'll have everything you kind of want. So before you get into modeling, it's important though to get your data into a format that can be used by your modeler. You have to define your problem, you have to pre-process things, and get it ready. And so we're going to do a bit of that before we even fit our first model. So a few things you want to ask yourself before building a model is, does our data have an output? I can't train a model to predict something that I don't have a label for. I mean, there's things like unsupervised learning that will help you do that, but a lot of times you want to predict like a score, and if I don't have my score column, it's going to be a lot harder. So we have to make sure all that's kind of there for you. Again, we talked about missing values. Especially difficult is when you have missing values in your target variable. What are you going to do with that? This way, you might want to keep them. They might be useful to you, especially for clinical data where missing values, it's a lot of your data, and so you wanted some way to impute those. But for us to make this simple, we're just going to take those out of our data set for now, and just deal with a target that has values defined.
Just another note on clinical data. I used to work with clinical data quite a lot. And when you're looking at data that comes from a study, sometimes just the fact that someone's dropped out of the study might mean something. And that's an entire, other foray into the data itself. That's another group that you want to consider separately. And the reasons why someone might drop out of a study are really important and might tell you a lot about the intervention that you were trying. So that can be a gold mine of interesting things to search for.
Okay, so the first thing, always the first thing you need to do is to deal with your target variable. The amount of times I've dealt with people who keep the target variable inside the modeling data set is a lot. And what you'll get great models, you get like 100% accuracy, 100% accuracy, but you're training on your target, so it's completely useless. So the first thing you need to do, I told you we got rid of the null values, but take your target variable out of your modeling data set. So this pop function does, it takes the whole score, puts it into another series for you, and gives you your model data back with the value removed. Kind of building off of that, data size 1 bane of existence is overfitting. You don't want to build a model that's super confident, and you're training it, it looks very great, and then you go to put it on some more unknown data and you get horrible predictions. And you're saying, I wasted 6 months and have a model that's not very good. And so there's ways to combat that scikit-learn provides. And it's kind of up to you use it properly. That's kind of a very important part of your job. So the way we're going to do this here, we're going to do a very simple train test split. And what that means is we're going to take our data, we're going to maybe take 20% of that out and put it to the side and just don't train on it. So we take maybe, if you have 100 rows, we take 20 rows out and keep 8 rows for training. Now notice that we're doing this first. I want to stress that. So you don't want to do that, in the modeling process. Because if you're comparing a bunch of models on different testing sets, then your comparison is completely useless. They're looking at different values. So the first thing you need to do in building a model is splitting up into these training test sets first, and then doing your modeling. So you can have each model can be trained on equal footing. Yes.
You generally do an 80-20 training.
Excuse me, can you
Do
repeat
you
that?
generally do an 80-20 split of data in the training?
So it depends on the data. Now, generally, depending if it's a small data set or if I can afford the computation power, I'll do a k-fold cross validation, where what that is basically you do that multiple times. So you have multiple training test splits across your data. And the reason we do that is like when you predict on a test set, you'll get a value. But you can imagine putting another test set and getting a different value. That's what we call variance. And you want to cut down on that variance, and the easiest way to do that, you'll see all across data science, is you take an average. And that's what k-fold cross-validation is doing, is taking an average over multiple test sets to make sure you're a little more confident for your error when you go on to new data. So that's in scikit-learn 2. This is all lies in the cross-validation folder of scikit-learn. There's k-fold cross-validation, and there's stratified k-fold cross-validation, which is useful for classification data that is unbalanced. You're going to want to make sure each of your tests and training partitions has the same amount of each target variable. So there's a lot there for you, but this train test split is the easiest thing to do. Also note, I just want to point out, you see that random state. It's very important when you generate this to make sure each one is getting the same indices from your data. And that's what that random state does. Meaning each time you run this code, it's going to give us the same train test split as opposed to different ones.
Yeah, so that your results are repeatable. Also note, there's 4 things here. There's train data, test data, train target, and test target. I've also seen people sort of, if they haven't set that random state, so they've sampled train data, test data, and then they don't know how to break up their target, and then they have to start at the beginning again. So breaking up your target is as important as breaking up your data.
Okay, so now we're not quite ready for modeling yet. We have to take care of all those pesky missing values and text variables and get them ready for modeling. That's what we're going to do a bit now. So for numeric values, for categorical values, models don't know how to deal with text. Like it doesn't mean anything to them. So we need to basically turn that into something that's usable. A common way of doing that, if you just have a multiple level categorical variable, there might be a level yes, no, and maybe. We just put those 0, 1, and 2. That's good for some models. Some models you actually go for your ordering, so you can do what's called monotonic encode them, but for this case, we're going to assume somewhat of an ordering and just do label them as some of these numeric values. So you can see here, here's a categorical variable. This is if we repeated primary school. So you can see they did twice, or they never did. So we have 3 levels here. And same with the mother's highest schooling, we have multiple levels here. So we're going to need to encode this from these text values to something numeric that the model can deal with. So scikit-learn has this preprocessing library and this feature extraction library, which will do exactly what I said, where it'll apply this kind of numeric encoding to these values. So we're going to use what's called a dict vectorizer, which is a fancy way of saying I'm going to take my columns and I'm going to assign them 0, 1, 2, and 3 based on the level. Now each of these feature extensions have the same, you use them the same way, where you call a fit on your training data and you call transform to get the actual encoding. Now I want to stress here is let's look at the flow of what's going on here, where we take our categorical variables and we fit on the training data, and then we transform both the training and the test data. We don't fit on the test data, we only transform on the test data. That's going to be a common theme, because you want to take, training, it's going to, for example, let's say we do some numeric scaling or something like that and we get the means on our training. We want to use that same mean on the test data. Or in this case, you might have an issue actually where, you get an extra variable or value on the test set. And that could screw up kind of the encoding. You might go from 0, 1, and 2, and that might shift it to 0, 1, 2, and 3 where they're different levels. So it can really mess up your model if you call fit on your test data as well. So missing values, so a lot of our numeric columns have missing values, and we're going to do probably one of the more simple ways to impute, and that's to do, and impute means replacing your missing values with the median. Now, I mean, a lot of people do the mean, but the problem with the mean is it can be very sensitive to outliers. It might be a lot higher or lower depending on, for example, in that case of having negative 999, if I calculated the mean there, it's going to be very low, when in fact it isn't. Obviously, you should take that out first, but if you didn't, it would be an issue. And so we use the median. That's kind of a more robust measure.
It could even be an issue if you are using the median. I mean, there's no substitute for a good, solid EDA. Do EDA early, do EDA often, do again.
Yeah, definitely. So again, you can see the use is very similar. We define this imputer object. We make an imputer object, tell it to use the median. We call fit on our training data, and we call transform on both the training and the test data. Oh, yes?
So we have a strategy for the median, so can you walk me through other strategies, like there's a mode strategy also, and
So there's a median, there's the average. You could also do something a little bit better by maybe you want to group by level. Maybe different levels have different medians and different averages, and depending on what level they are, fill it with that particular one. Or you could do very fancy statistical models to come up with some general thing. But so I think the most common other one to move beyond just a median would be to do it by a grouping level, which they might be very different. Oh, also, when you have time series data, for example, the ordering matters, so you might have some trend in the value, and you could you could fit a polynomial, for example, on that trend, and then kind of impute the missing values there. That's another popular strategy for time series. Okay, so we've kind of filled in the missing values, we've dealt with our encoding of our categoricals, so now we're going to put that all back together and get ready for modeling. So NumPy has this H stack, it stands for horizontal stack, and all it does is it takes 2 arrays and squishes them together into one array where our categorical variables on one side and numeric on the other, and it's one big matrix we can just go ahead and use for modeling. Okay, so let's build our first model. We're going to take probably the most common one, which is linear regression. Still a great model, still always a good choice to kind of just get a feeling of how things are working. We use, it's a linear model package. You can just import linear regression. Here I've kind of showed you that a lot of them have default values that you can mess around with. In this case, I've set the fit intercept to false. I wouldn't ever recommend actually setting the fit intercept to false. I just kind of wanted to show that, there's some things you can mess around with to change the behavior of these models. So to use a model, it's actually very simple. You just call a fit on the training data as your predictors, and then the train target is your target. So it goes predictors first, target second. and they'll fit your model. Linear regression is just coefficients in front of you predictors, summing them up, and that gives you your target. So, and then to make a prediction, just call .predict on, in this case, we're doing it on our test data, and we store that into a series. So you see how it's easy to go from NumPy arrays back to series, just fill your series with the predictions and give it a name.
So could you use linear regression to find missing values?
You repeat the question.
Yeah, so he asked if you could use linear regression to find missing values. And so it depends on what you're doing. For example, when I was mentioning the time series data, you might want to take a linear line on a particular column to fill out, maybe there's some, you could connect the dots almost there and fill values like that. So yeah, it's a strategy you can use. Like the one problem is I'd avoid, you have to be very careful for fitting a model and then filling the QD values when you've already looked at your target, because you are biasing yourself that way, right? So you got to be very careful whenever you build a model and fit it and you put in your data, you bias yourself already. That's one way to overfit to your data. Okay, so one easy kind of straightforward way to look at the results of your model is to kind of take the predictions of the model and plot them against the actual values in your test set. So what we've done here is we've taken each row in our data set, looked at the actual value, put that in on the x-axis, and the y-axis looked at the predictions for a model. And you kind of expect, like, if we did very well, it would almost lie on a line. The actuals would line up with the predictions. But it also kind of gives you an idea of where we're doing well and where we're not doing well. So you can see on actual around 30 or so, we're doing okay. We're good, we're fitting roughly 30 is 30. But however, if you go up to like 40 and 50, you can see here, 40 is getting predicted as 30. So it looks like we're not doing very well, at these kind of tail ends of our distributions here. So that's kind of one way these models are kind of failing us, or not doing as well as they could be. Quick graphical look at what's going on.
Emphasis on quick graphical look. So when I look at this, one of the first things I see is, okay, look at this actual, and the axis goes all the way to 70, and then this one's going to 50. One of the things that I'd like to look at when I'm looking at predicted versus actual here is I kind of want to draw a 45-degree line and then see, just in general, not looking at any particular intercept of values, are we predicting mostly high or mostly low, and could I live with that if I was going to use this model in production? And so right now it's just immediately difficult to see that. But I want to draw that line at 45 and then look at the trend of predictions, whether something's doing high or low, because you could also see something that has like a very nice line, but that line is at the wrong angle, and then you're still sort of lost.
Yeah. So this kind of works, for one model, but how can we really tell if this model is good versus other models and stuff like that? You kind of want like one value kind of to tell you like, oh, this model's doing great, but this model's not doing great. And so, there's a lot of different metrics. These are these single scalar values you can use to compare models. And we took a bunch of them. You might, when you're first starting modeling, pick one, focus on that. It's kind of nice to kind of get an idea of different ones because they kind of tell you different things. A lot of these ones that use the median are very less prone to outliers, and they've been ready to focus on the main part of the distribution, unlike squared error, which is going to be very skewed by outliers and will be a lot bigger, if you have a lot of problems there. I like explain variance for linear regression. It kind of tells you like if you pick the mean, you wouldn't explain any of the variance around that and the different values that are the mean, and you'd expect your learner to kind of learn those differences. And so the more you pick up, the better your learner's going to do. It's intuitive from that. But again, so numbers tell you so much, and really, every time I start modeling, I don't do linear regression. What I do is I take a very dumb model and fit that first. For example, I might just predict the mean, or I might just predict the median. And that's good because like you might get a value for your very complex neural network that gives you, an RMSE of 30 or something like that, and you're like, oh, this did great, this is wonderful. And it turns out if you just predicted the mean, you get an RMSE of 40, and like, why did I spend this time building my neural network when the mean was a great predictor or something like that, or a simple linear regression. So it's very important to take those dummy models and, they are important. They tell you kind of how complex your data is or how complex your models have to be. And so that's what we do here. We took the mean response and we took the median response of the target of the training data, again, not the test data, the training data, and use that as a predictor. You can see we've made this report, and you can see the explaining variance, as I said, for the mean response is 0. We're not predicting anything besides the mean. However, for the linear regression, we've kind of picked up roughly 30% of the variance, which is not bad. That's pretty good. But let's see if we can kind of explain a little bit more with some more complex models. So the next model, I won't go too into it, but this is kind of a nice little stepping stone above linear regression, and that's the elastic net. And so what the elastic net is doing is it's kind of giving you some basically loading of your coefficients. We kind of said we have a bank of values that your coefficient come up with a maximum value, and you kind of have to distribute that, dole that out among the coefficients. And so when you get into more complex models, you're kind of faced with these parameters that you have to tune. They're kind of like switches, this alpha value and this L1 ratio. And a lot of times it's not clear what the best value of alpha or L1 or a tree depth or this, the architecture of your neural network is. So you have to kind of do some exploring. And one way of doing this is called grid search. And scikit-learn kind of provides a nice little interface for that. It's in the grid search package. And what you can do is you can say, I'm going to try an alpha value from 0.1 to 2, and 10 different values of that. Now a ratio of 0 to 1, and 10 different values of that. And we'll go through each combination of that, fit a model, do some validation for you, and pick the best parameter based on that validation. And so you can just use it like regular estimate. You say, here's my estimate I want to fit. That's the elastic net. The parameter grid I want to tune, and just call fit. And we'll do all that work for you and give you the best value from your training data. Again, notice how we did grid search on training data. We didn't, take our training data and then validate on the validation data. That's for later. This is still the model building process. All the model building process needs to be done on the test data, even the grid search, for a proper comparison.
Yeah, just to explain that in a different way, these parameters, it's like kind of going into airplane cockpit, and then there are some knobs that don't have labels. They're like very non-intuitive, and so when using these non-intuitive things, what you really want to do is just think about, you don't want to really say like brute forcing, but it's like finding local maxima, where basically in a certain space, which you define as reasonable, here we've done these ranges. We want to say, okay, in this reasonable space based on prior experience with looking at this kind of model and these parameters, I think we can try all the things in here, and then anything that is like doing the best in this range is something reasonable that makes sense, and we can move forward with that.
So one thing I want to point out here that we messed up on is the fact that we didn't set a random state here. So if you use this grid search object on a different thing, it's going to partition your data differently. The comparison's not going to be fair. So again, I'm going to stress, always say random state, so each time you do a comparison, it's the same comparison, it's trained on the same data, otherwise it's completely meaningless. Okay, so we've made this actual versus predicted again, and see if it's changed at all from the elastic net. You kind of see here, it's a little bit better just looking at the Pearson's R, which is kind of saying the correlation between the variables, but it looks kind of the same, for the most part the same. To get a better idea, we could go out and look at our little metric report here. And we can see that the explainer variance is 0.01 a little bit better. The RMSE is a little bit lower. So it's learning something a little bit more over normal linear regression, which is kind of expected just because it's kind of a smarter linear regression, kind of think of it that way. But the beauty of scikit-learn is we have so many models and they all have very similar APIs. So might as well just throw something complicated at this guy. And so we chose a random forest, which is a nice little kind of coverall estimator. It's very good at dealing with different types of data. You don't need to do a lot of complicated categorical encoding or scaling numeric variables. It'll be very good at handling that. And so what random forest is, it basically takes a decision tree, which is like, is it male or female, yes or no? If it's female, I'll pick one value, male, I'll pick another, and kind of go and iterate on that. And it takes a bunch of those, and again, a single decision tree, overfits like mad if you've ever fit a single decision tree. And so to combat that overfitting, which is variance, we take averages, and that's what a random forest does. It takes an average of a bunch of different decision trees, growing on different subsets of your data. And so that's what these kind of two parameters are: the number of estimators and the number of base decision trees you're growing. And then depth is telling you how deep those individual decision trees are. The deeper your tree, the more you're going to overfit, the more complex your model has. And so, it's kind of a trade-off between like, oh, do I want to go this really deep and, maybe I'm going to overfit, or do I want to go, a little less deep and get a better score? And so we kind of we don't know, so we tune, and we use grid search and we fit it and do the same thing over and over again. And so again, predictive versus actual. This guy looks, actually a little different, which is nice. We kind of see like, oh, we're doing a little bit better at the bigger values. At 40, I'm at least getting up to 40. Before I wasn't even predicting 40, I was predicting like 30, so this is a little bit better. And to get an idea of that, again, we can go to our metric report. And we can see like, okay, the random forest is, explaining a little bit more. It's a lot better than linear regression, but not, not much. I mean, it's a little bit better. And so the thing you might want to ask is when you're building models, you're not only asking, maybe you don't want, the best score. Maybe you want to predict one model is doing well at some particular space, another model is doing well at another particular space, so you might want to use different models depending where you're at. And so we could ask ourselves like, so maybe the random forest is doing well at, high score values, and maybe, the linear regression is doing good at, mid-level values, and you can kind of pick and choose which one we want to use or something like that.
Yeah, that's very, very important with a lot of the people that we work with DataRobot, where they're interested in a model that say predicts something for some subset of their client database or something like that, and they're interested in something that performs well on the high end or the low end. And I would say more often than not for certain data sets, you'll see it's very tough to get a model which predicts high end and low end both very well. So looking at sort of those trends and then those subgroups is one of the biggest parts of kind of doing, it's almost like exploratory model analysis, EMA, something like that.
Yeah, and if any of you have dabbled a bit in Kaggle, this is a very common thing to do to decide what you're going to blend together. You want to blend together different models. Models that behave differently. We're familiar with that. So here's a nice little plot you can do to kind of see where they're performing differently or not. You kind of take the difference between your predicted and actual values for each row and plot them against each other. We do that for the linear regression and the random forest. You can see they kind of line on line. So it looks like they're kind of doing the same little thing, and not much different overall. They're making the same errors. Okay, so how can we improve these models? We can keep building more and more complex models and hoping we're going to get better. Or maybe we want
infinite depth for your
infinite depth, yeah, infinite depth, infinite deep for deep neural networks, But truthfully, like maybe we want to build maybe we want to use a linear regression model or something like that, and like we don't want these super complex models. Maybe we could do some feature engineering. Maybe we could make some features that are a little bit better, and we can deal with our elastic net as opposed to our 15 deep random forest or something like that.
Another thing that's important when selecting one model versus another, sometimes we'll see people actually really want to use a model which performs well but isn't the absolute best model, and that's because of interpretability. So some models which might do really well, say your crazy deep neural net, will be very tough to get insights from if you need to communicate the results to someone else. So sometimes the best model isn't always the best model.
For example, we have some clients, who are, dealing with insurance data. You don't want to tell someone to deny insurance because my deep net said so. You want to say like, oh, it was because like you had this, this many car accidents this year or something like that. So okay, so we're gonna do kind of basic feature engineering. You could really go crazy here. This is where EDA kind of like really comes in handy, where you might see some things you want to make and try and put into your model. But a nice, easy thing to do is just to take quadratic combinations. What I mean by that is you can take one feature, multiply it by another feature, or the same feature and multiply it by itself. So that's useful, for example, if you have a linear model and you wanted to predict something that's a curve, like a quadratic curve or parabola, and you could get a linear model to do that by just saying like, oh, instead of predicting x, predict x squared, and then you're going to get a parabola. And so that usually helps a lot with linear models. Scikit-learn makes that super easy. You have this thing called a pipeline, and what a pipeline does, it says like, okay, I want to first do polynomial features, in this case of second degree, i.e. x squared, and then I want to take those features and feed that into here's a lasso, which is a form of a linear model. So elastic net is a combination between lasso and bridge, and the lasso is just a particular one end of that. And so you can just make a pipeline and call fit on that pipeline, and it'll do the polynomial feature extraction and the fit of the lasso, which is useful if you're doing something like a grid search, right? Because a lot of times when you're doing grid search, you want to tune the whole pipeline. You don't want to just tune the particular estimator. So this is a way of defining one big estimator that can tune multiple parameters at the same time. And so again, we've made our prediction versus actual. Kind of hard to see, if there's a difference. It looks like there's a little more linear relationship, so it looks like we're doing a little bit better. And again, we can look at our metric report. And we see, oh, look, our polynomial SU, which is a linear model, is doing better than a random forest. And all we did was project features, So, feature engineering can be pretty powerful, if you know what good features or if you play around. I'd say a lot of the time is going to be spent, trying a model, going back, doing some feature engineering, putting that into a model and iterating, and kind of going crazy with it. If it doesn't work out, it doesn't work out, and just try something else.
Yeah, sometimes feature engineering is full of stuff that seems sort of random, but then also, this is important when data scientists come and approach a problem with this amount of domain knowledge, maybe from things aside from modeling. They can come in and then say, okay, well, maybe we want like a 3-day trend on some of this, and we're going to wrap that into a variable, like a very simple sort of feature engineering task, which they might know will perform better just given that. So I would say it's a mixture of some seemingly random stuff, some magic, and domain knowledge.
And some models too, need feature engineering that perform better. Linear models need these quadratic terms to pick up, because they're not going to pick up on quadratic terms by themselves, or a random forest will, or and things like that. So feature engineering is important to get similar performance for some of these models.
Yeah. I have a question. So it's not related to Python, but it's sometimes easy to get lost in just applying those things as commands. How important is it for you guys as a data scientist to be on top of your math for that thing? I mean, to know exactly what a random forest does, exactly what a polynomial SU does. I mean, do you think that's key, or
Yeah. So actually, no. You could go and kind of plug and chug and just kind of learn what works. But for example, like if you're training something like a neural network, you know that the way that thing works is it needs standardized data. That needs to be normalized, or it's not going to work. You learn that by just playing around, or you can just know how it works a bit and just know that immediately. Also, things like a random forest, when they make splits, they don't really know, for example, the difference between features and the ratio between features. And so that's a nice feature to give forest models, actually, that reduce performance just because of the way they define this tree structure. And so it's nice to know a little bit about how they work and kind of guides you what features you want to add, or you don't.
Another thing that we find though that's kind of dangerous is people who only use models that they understand really, really deeply, and then that kind of limits them from other approaches where perhaps a shallow knowledge of another approach, another model, might have actually given them better results than their really deep knowledge and perfect tuning of the one modeling technique they're really comfortable with. So I would say they're kind of both. You want to have both skills in your tool bag. You want to be able to plug and chug on approaches and use common sense with things that you're not familiar with, but definitely try them, use them as baseline, stuff like that. But then obviously having really deep knowledge of one or two approaches, some of the main ones, like the ones that we're using here, elastic net, random forest, those will be your go-tos, but you should try other things as well.
Yeah, and you can always try a bunch of them, and the one that works best, then you can go deeper into it, and then optimize further. So it's just to try a bunch of things, you probably don't need to know everything.
Exactly. So both deep and shallow knowledge, and having the confidence to kind of move forward on both is key.
Okay, so we've done all this modeling and stuff like that, but we can obviously do more. This is a huge data set, we've only kind of started, looking at it. So there's a lot of things we could do. We could try more variables. We tried, I think, 6 columns, something like that. We didn't try a lot of this data set, so we can obviously improve there. Try different transforms through data, and we got this quadratic. But maybe, as I said, we had some skewed data, so maybe we want to make that, apply some transformation to make it normal, and that might improve some performance and stuff like that. Try different models, try different parameters for the models too. We only tried a few. Maybe we want to try now that we know that a random forest does very well. We want to fine tune that. We want to grow deeper trees or something like that.
And a deeper grid search.
And a deeper grid search takes a very long time. So yeah, going back and tuning more is always very useful. Okay, to wrap up, we think Pandas is great. It's just wonderful for dealing with data. The reads, I can't stress how magical that read CSV function is. That you can just take a lot of different forms of data and read it into one data frame. That
Try doing that by hand, or using tools that predate Pandas, wow.
A lot of us have nightmares of trying to get our data into Python, so it's a wonderful tool. Matplotlib and Seaborn for making plots. Seaborn in particular makes it very easy to look at these. We looked at a bunch of distributions, very simple, one-liners almost, to get a very good idea of this data set. And then scikit-learn, so many tools. We only push the top of the iceberg. You can really go into that level, and there's a lot of cool things you can do.
All right, thank you so much. We posted our IPython notebook. You can recreate these slides. If you want to make a change or something interesting, feel free to submit a pull request.